The researchers' interest in this topic emerged from a broader societal shift that is reshaping education at every level. Artificial intelligence tools are now widely accessible to students, including generative writing assistants, feedback tools, and automated revision supports. Educational institutions are increasingly required to make policy decisions about AI use that affect instruction, assessment, academic integrity, and equity. These decisions extend beyond individual classrooms and influence how institutions define learning in an AI-saturated world. This creates a central tension. Policies regulating AI use are being implemented rapidly, yet the empirical evidence needed to guide those policies, particularly evidence focused on learning outcomes, remains limited and inconsistent. This tension is evident in the literature on AI-supported writing and learning. Some studies suggest that AI tools can enhance learning by supporting feedback, scaffolding revision, and aiding idea development. Other studies raise concerns that AI use may reduce cognitive engagement, promote surface-level writing, or disproportionately benefit students who already possess stronger academic skills. A closer examination of this literature reveals a recurring problem. Students who use AI tools often differ from those who do not in meaningful ways, including prior writing ability, confidence, and familiarity with technology. When these baseline differences are ignored, conclusions about AI effectiveness may reflect who students already were rather than what AI use contributed to their learning. Much of the existing research evaluates AI effectiveness by comparing raw post-intervention writing scores across groups. While these comparisons are common, they risk conflating AI use with pre-existing differences. If one group begins with stronger writing skills, that group may also end stronger regardless of instructional approach. As a result, the literature lacks sufficient evidence addressing a more precise and policy-relevant question. When students begin at different writing levels, do writing outcomes still differ across AI use conditions once those baseline differences are taken into account? This study is situated within a post-positivist worldview, which assumes that educational outcomes can be measured, that patterns can be examined using statistical methods, and that findings represent probabilistic rather than absolute truth. From this perspective, the goal is not certainty, but the reduction of bias and the development of more defensible conclusions using empirical evidence. The study is guided by self-regulated learning theory, which conceptualizes learning as an active process involving goal setting, monitoring understanding, using feedback, and adjusting strategies. Learning improves when students plan their work, monitor clarity, respond to feedback, and revise intentionally. Tools can either support or undermine this process depending on how they are used. AI tools may function as scaffolds when integrated with instructional guidance, but they may undermine learning when they replace cognitive effort. This framework supports examining not simply whether AI is used, but how it is used instructionally. Because the outcome of interest is writing performance measured numerically, and because the goal is to compare outcomes across instructional conditions, the research problem is inherently quantitative. The study does not explore students' perceptions or experiences, which would suggest a qualitative approach. It does not attempt to predict writing outcomes from multiple variables, which would suggest regression. Instead, it focuses on determining whether statistically significant differences exist across groups while accounting for known background differences. The overall research design is a quasi-experimental, non-equivalent groups design. This design was chosen because random assignment to AI use conditions was not feasible or ethical. AI use policies were established at the course level prior to the study, making random assignment impractical, without disrupting instruction. As a result, groups were non-equivalent by design, meaning baseline differences were expected rather than avoided. This design allows examination of authentic instructional practices, while acknowledging limitations in causal inference. Participants were selected using purposive sampling. Course sections were intentionally chosen because they had clearly defined and consistently implemented AI use policies aligned with the research question. This sampling strategy was appropriate because the goal was not broad population generalization, but focused comparison of specific instructional approaches in real educational contexts. While purposive sampling limits generalizability beyond similar settings, It strengthens internal coherence by ensuring that group differences reflect meaningful instructional distinctions, rather than accidental variation. Because groups were intentionally selected and not randomly assigned, baseline differences in writing ability were expected. This design feature directly informed the analytic strategy. Comparing raw group means would risk attributing differences to AI use when they may instead reflect where students started. For this reason, analysis of covariance, or ANCOVA, was required. ANCOVA is appropriate when the research question involves comparing group means on a numeric outcome, while statistically controlling for a numeric background variable. The research question does not call for correlation, because it is not focused on relationships between variables. It does not call for regression, because prediction is not the goal. It does not call for ANOVA alone, because raw group comparisons would ignore baseline differences. ANCOVA allows group means to be compared as if students had started at the same baseline level, supporting a fairer comparison. The purpose of this quantitative study was to examine whether students' post-intervention writing performance differed across AI use conditions while controlling for baseline writing ability. Using a quasi-experimental nonequivalent groups design, the study employed ANCOVA to evaluate adjusted group differences. The research question guiding the study was: is there a statistically significant difference in mean post-intervention writing scores among students in different AI use conditions, while controlling for baseline writing scores? The null hypothesis stated that there is no statistically significant difference in adjusted mean post-intervention writing scores among the AI use conditions when controlling for baseline writing ability. The alternative hypothesis stated that there is a statistically significant difference in adjusted mean post-intervention writing scores among the AI use conditions when controlling for baseline writing ability. In this study, the independent variable was AI use condition. This categorical variable represented the instructional context under which students completed their writing tasks, and consisted of 3 independent groups: no AI use, guided AI use, and unguided AI use. The independent variable reflects an instructional decision, rather than a student characteristic. The dependent variable was post-intervention writing performance. This outcome represented the learning result of interest, and was operationalized as a total score derived from a standardized writing rubric. Because the rubric produced numeric scores reflecting degree of writing quality, the dependent variable was continuous and appropriate for mean comparison. The covariate was baseline writing ability. This variable represented students' writing performance prior to exposure to AI use conditions, and was measured using the same rubric as the post-intervention score to ensure consistency. The covariate was included because prior writing ability is known to influence later writing outcomes. Including baseline writing ability does not remove its influence. Instead, it allows the analysis to account for it so that group comparisons focus more directly on instructional differences. Students completed a baseline writing task in Week 2, engaged in instruction under their assigned AI use condition during Weeks 3 through 10, and completed a final writing task in Week 11. Each student completed their own work independently, and appeared in only one AI use condition, supporting independence of observations. Writing performance was measured using a rubric assessing organization, coherence, argument development, and mechanics. Each rubric dimension was intentionally aligned with self-regulated learning behaviors, such as planning, monitoring clarity, responding to feedback, and revising intentionally. Scores across dimensions were summed to create a total writing score. Reliability was addressed through inter-rater procedures. 20% of writing samples were double-scored. An intraclass correlation coefficient of 86 indicated strong agreement, meaning different raters scored the same paper similarly enough that the scores can be considered stable. Internal consistency across rubric dimensions was also strong, with a Cronbach's alpha of 82, supporting the use of a combined total score. Validity was addressed through multiple strategies. Content validity was supported through expert review, which resulted in refinement of the argument development descriptor. Face validity was supported through pilot testing, during which students reported that rubric expectations were clear. Construct validity was supported through moderate correlations among rubric dimensions, consistent with a unified writing construct. Criterion-related validity was examined by correlating rubric scores with a departmental writing benchmark, yielding a correlation of 68. Before analysis, data were screened and ANCOVA assumptions were evaluated carefully, because the validity of adjusted comparisons depends on these conditions being reasonably met. The assumption of independence requires that each student's score be generated independently, and that no student contribute data to more than one group. This assumption was met because each student completed their writing individually and group membership did not overlap. The measurement assumption requires that the dependent variable be numeric and measured consistently across groups. This condition was met because all writing samples were scored using the same rubric, scale, and rater training procedures. The covariate relevance assumption requires that the covariate be numeric and meaningfully related to the outcome. Baseline writing ability significantly predicted post-intervention writing performance, indicating that students who started stronger tended to end stronger. This confirms that the covariate explained meaningful variation and justified its inclusion. The normality assumption requires that writing scores within each group cluster around an average without extreme skew. Group-level normality tests were not statistically significant, with p-values greater than 0.05, indicating no strong evidence of non-normality. Because ANCOVA is robust to minor deviations, this level of normality was sufficient. The homogeneity of variance assumption requires that the spread of scores be similar across groups. This was examined using Levine's test, which compares group variability. Levine's test was not statistically significant. F with 2 and 86 degrees of freedom equaled 0.76, and the p-value was 0.47. Because this p-value is much larger than 0.05, the test did not detect meaningful differences in variability across AI use conditions. In practical terms, the groups had similar score dispersion, supporting fair comparison. The homogeneity of regression slopes assumption is the most critical additional requirement for ANCOVA. This assumption requires that baseline writing ability relate to post-intervention writing performance in a similar way across groups. This was tested by examining the interaction between baseline writing score and AI use condition. The interaction was not statistically significant. F with 2 and 84 degrees of freedom equaled 0.49, and the p-value was 0.62. A p-value far greater than 0.5 indicates that the data do not provide evidence that the relationship differs across groups. Any small differences observed are easily explained by random variation, confirming that the ANCOVA adjustment is appropriate. Scores were also reviewed for extreme outliers, and none were identified that disproportionately influenced results. Descriptive statistics showed baseline differences across groups, reinforcing the need for adjustment. Raw post-intervention means also differed, but these values alone were insufficient for interpretation because they did not account for where students started. ANCOVA adjusts group comparisons by removing the portion of post-intervention performance associated with baseline writing ability. Adjusted means therefore represent what outcomes would look like if students had started at the same baseline level. The ANCOVA produced an F statistic of 4.18 with 2 and 86 degrees of freedom, and a p-value of 0.018. A p-value represents the probability of observing a result at least this extreme if, in reality, there were no differences among the adjusted group means. The decision rule used in this study was that p-values less than 0.5 indicate a statistically significant result. Because 0.18 is smaller than 0.5, the null hypothesis was rejected. This indicates that after accounting for baseline writing ability, the adjusted mean writing scores across AI use conditions were not all the same. The covariate was also statistically significant, with an F statistic of 31.42 and a p-value less than 0.001. A p-value this small indicates extremely strong evidence that baseline writing ability is related to post-intervention writing performance. This confirms that students' starting writing skill explained a substantial portion of outcome variation, and validates the decision to include baseline writing ability as a covariate. Post hoc comparisons of adjusted means were conducted using a Bonferroni correction. 3 pairwise comparisons were tested. The guided AI group scored significantly higher than the no AI group, p equals 0.005. Differences involving the unguided AI group were not statistically significant. Effect size was examined using partial ETA squared, which represents the proportion of variance in post-intervention writing performance associated with AI use condition after controlling for baseline writing ability. The value of 0.9 indicates that approximately 9% of the variation in writing outcomes was linked to how AI was used instructionally rather than to where students started. In educational research, this constitutes a small to moderate effect. The adjusted mean difference between the guided AI and no AI groups was 4.6 points. The 95% confidence interval for this difference ranged from 1.3 to 7.9 points. A confidence interval provides a range of values within which the true population difference is likely to fall. Because the entire interval lies above 0, the difference favors the guided AI group and is consistent with the statistically significant ANCOVA result. In practical terms, this suggests that guided AI use is associated with an improvement of at least about 1 point, and as much as about 8 points on the writing rubric. These findings align with self-regulated learning theory. Guided AI use appears to support planning, monitoring, and revision processes, while unguided AI use does not produce the same benefit. The statistical results therefore reinforce the theoretical expectation that instructional structure matters. Several limitations should be considered. The quasi-experimental design limits causal inference because students were not randomly assigned. Purposive sampling limits generalizability beyond similar instructional contexts. Measurement of AI use compliance may not have captured all variation in student behavior. Writing outcomes were measured over a single instructional period, limiting conclusions about long-term learning or skill transfer. Despite these limitations, the analytic approach strengthens confidence in the findings. By explicitly addressing baseline differences through ANCOVA and carefully evaluating assumptions, the study reduces common sources of bias in educational research. The findings have important policy implications. Institutions should avoid treating AI use as a binary decision. Evidence suggests that guided integration supports learning more effectively than unrestricted access or blanket bans. Policies should emphasize instructional scaffolding, faculty development, clear expectations for ethical and productive AI use, and equity in access to guidance. Future research should examine AI-supported writing longitudinally to determine whether observed gains persist and transfer to AI-free contexts. Experimental or matched designs would strengthen causal inference. Additional covariates such as digital literacy, motivation, and prior AI experience should be examined. Future studies should also explore outcomes beyond writing performance, including metacognitive development and independent learning behaviors. In summary, this quantitative case study demonstrates how a quasi-experimental non-equivalent group's design combined with purposive sampling and ANCOVA can support fairer conclusions in real-world educational settings. After controlling for baseline writing ability, guided AI use was associated with higher writing performance, highlighting the importance of instructional structure in AI-supported learning.